Alright, part A. Draw the free body diagram. Okay. This is the free body diagram. This is the applied force. This is the frictional force acting against the block sliding. This is the gravitational force pulling the block down into the ground, and this is the normal force from the ground pushing the block up. The reason the normal force is so huge is because there are two downward forces acting on the block. The vertical component of this force right here acting down, and the gravitational force acting down. Since the box is not accelerating vertically, then that means that the net force in the y direction must be 0. So the force pushing up on the box must be equal to the force that's pushing down on the box. And that's why Fn is so big. Part B. Using the data table, indicate below which quantity should be graphed to yield a straight line to use to calculate the acceleration. Okay, so what we know about a straight line is that its equation looks like this, right? Y equals mx plus b. But with displacement equations, it's not that. Displacement equation looks like this. X equals VIT plus 1/2 AT squared, right? Now, because we are told that the box is initially at rest, then we can just set VI equal to 0, so this just the entire part just gets like deleted. And so for this situation here, the equation would be x equals 1/2 AT squared, because again, there's no initial velocity. And so what we need to do is turn this into this. Now, to do that, we need to know what our variable is and what our slope is, right? So the variable here, x, would be equivalent to t squared in this equation. And the slope m would be 1/2 a. Because on a graph, the x-axis, like for these problems, the x-axis is always t. And so we're going to replace x with t squared here, and then m with 1/2 a. And of course, x would be the equivalent to y in this situation. And we don't have to worry about this plus b part because initial velocity is 0. And we can fairly assume that it starts at 0 too, like position-wise. And so what we can do is draw out the table, which is the next little part of b. Oh yeah, no, wait. Vertical axis is x, of course. And again, horizontal axis is t. And then now we can do the table. Okay. So I'll just start labeling these, the initial values given first. So these are the values given to us by the table so far, right? And again, in order to turn this into this, the x here would have to be t squared, and the m would be 1/2 a, and then the y would be x here, right? And so what we need to do is square these t terms, and then make that our x. And so it would be, because this is t squared, so just square all of these, and of course the position would stay the same. So we can just write that down again. The position values stay the same, and then we're just going to square all the t values and put them down here. calculator. All right. So these are all of our t squared values, right? So this is just this squared, 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 and this is just this squared. This here says delta t squared parentheses s squared, right? Because it's in seconds. And so that's our data table, and that's what we can use to find the acceleration. Because what is acceleration? Usually the unit would be mass, meters per second squared, not mass. And so that's why we have seconds squared here, and then the position stays the same because the position is already in meters. So meters over seconds squared gives us the acceleration. So we're good on that. All right. Part C, plot the data points on a graph. So just gotta look at the table here. All right. Then plot the points. All right. These are the points and the graph. So the x starts at 0.036 there, and then it ends at 1.521 up here. And then for the t, or the t squared, it would start at 0.04, which is way down there, very small, and ends at 1.69. And then these are the points plotted right along this axis, and then draw a line that best represents the data. Okay. Let's see. Right about. All right. My pen tip was a little thicker than I thought it would be, so I didn't get exactly the point I wanted, but this is what I did. My best fit lines kind of suck, so hope that's at least a little close to satisfactory. That's the first point right there, by the way. It's very, very small. Second point, third point, fourth point, fifth point. Okay, moving on. All right. Part D, calculating experimental value for acceleration using the straight line. Well, my straight line is supposed to be something that's close to this divided by this. So we'll just use that value because I really don't want to use mine. And also, I don't even know how I would find the slope of this thing without using Desmos. I don't even think I'm allowed to use that. So, okay. So, this is 1.521. This is 1.69. Divide that, you get, okay, you can't see that, but it's 0.9. And so, as we said earlier, this is the slope. 1/2 A is the slope, right? The slope of what my line is supposed to be is 0.9, and so we set 1/2 A equal to that. Like that, right? Because 0.9 meters seconds squared, that's our slope of the line here. And so, in this form. And so, we set 1/2 A equal to 0.9. Divide both sides by 1/2, and you get A equals 1.8 meters per second squared, like that. So that's our value for A. And then using Newton's second law, derive an expression for the coefficient of friction. Okay. So, go up here. On this block, there is the applied force and friction. So just write that out. The equation for the net force should be this: F cosine theta, right? The horizontal component of the applied force here, minus mu k times the force of gravity plus F sine theta, which is the vertical component of this thing, right? Because the vertical component of the applied force plus Fg equals Fn, the magnitude of Fn, and then multiply that by the coefficient of friction, you should get the frictional force. And so subtract that from F cosine theta, and you should get your net force. And so from here, since we're solving for mu k, we can add that term to both sides. And then subtract ma simultaneously. Like that. Right, just switch them around. And then divide both sides by mg plus F sine theta. So mu k equals F cosine theta minus ma over mg plus F sine theta. Part F, we are given values. Find the kinetic frictional force, plug them in. So just use this equation that we found earlier. 12 cosine 60 minus mu k times mg plus 12 sine 60 equals the mass 2 times the acceleration 1.8. And then from here we can also just use this mu k equation, right? So mu k equals mu k equals that, right? 12 cosine 60 minus 2 times 1.8 over 2 times 9.8 plus 12 sine 60. And then plug that into your calculator. 0.08. So that's the 0.08 here. That's the coefficient of friction. So just multiply that by this stuff. Times mg plus sine 60. Put that into your calculator. 2.4. So the frictional force Fk equals 2.4 newtons. Right there. And then using given values, calculate the numerical value for the coefficient of friction mu k. I honestly did not know how to find Fk without finding mu k first, so that's what it is. Mu k is 0.08. If the angle theta is decreased, on per h, if the angle theta is decreased, what effect does it have on the acceleration of the block? Okay, so let me draw the diagram out again. This time with theta here. Fn, Fg. Alright, so this is the diagram of the motion here, right? If we were to decrease this angle, right, decrease angle theta, like it says, then the vertical component of the applied force would decrease, because, I mean, it would look like that. It would literally go down, right? This part would decrease. And so there's less force acting downward on the block. If there's less force acting downward on the block, there is less force acting upward on the block. Now, the frictional force here entirely depends on the coefficient of friction, which in this case would stay the same, and the force that's acting upward on the block, right, which is equal to the two forces acting downward on the block. And so this would decrease if this decreases. If this decreases, that means that Fn decreases, meaning that Fk decreases. And so if Fk decreases, then the acceleration would go up because there's less force acting against the block's motion. So if theta goes down, A goes up. And then sketch graphs. All right. Acceleration versus time. Okay. Redo that real quick. This is the acceleration graph. Right, the acceleration remains constant. And the reason the acceleration is constant is because, well, it's just 1.8. I mean, right here. But also we can say that the position graph looks like a parabola, and we needed to turn it into a straight line. If it were a straight line in the first place, we wouldn't need to do any of this stuff. And so if we needed to turn it into a straight line, then it would have been a parabola at first. Take the derivative of a parabola. It's a tilted line, tilted slope like this. Take the derivative of this. It's just a straight line across, right? So that's why A is like that. J, velocity versus time. Looks like that. velocity time looks like this, because it's increasing due to acceleration, so it's not just going to be a straight line, and obviously it exists, but here it's 0 because we are told that the whole system starts initially at rest, and so that's why VI is 0 here, and this slope would be 1.8, just like the acceleration is. And then K, the x of t graph, position time graph. Would look like this, because of course this is squared, so it will be a parabola shape, right? And then it starts at 0, VI starts at 0 as well. This is the derivative of this, this is the derivative of this. And so yeah, that's the x. Oh yeah, and I labeled all of them 0 to 1 to 1.3 because that's the time interval given right here, up to 1.3. So yeah, thank you.